Thank you. So, hello everyone, and I'm very happy to be here and I'm a little bit embarrassed to present after Tommy, if I can, because he set the stage and the bar very high, I would say. And just to start the introduction, I'm not Antonov Meister. He was supposed to be here, and he's here. Basically, he flew here for this speech and the presentation. But this morning, because the reality is always bigger and more augmented than what we can do with the extending it or augmenting it, he found himself in a big reorganization inside ST at executive level. So he's part of a conf call with the CEO now, and he asked me to present on his behalf. So I'm not taking the credit of the slides. I will take the debit of destroying them. But I take this as an experience I got this morning. Basically, I woke up to be there, as you guys, listening to Tom presenting and those great speakers presenting. And when I got the request to present myself, a little bit of anxiety and what should I do? And the idea of a metaverse where I can send here my puppet presenting my avatar was really intriguing me. But on the other side, I was kept on thinking that, again, reality is bigger. And it's for me a big opportunity to be here, to present to you, to meet the great speakers. And we are in a great place, human-centered. It's a human-centered design. So humans are at the center. We have a big responsibility. I believe Tom was very clear, and I love what he did. I saw last week the AWE, Augmented World Expo, presentations on what the technology can do. I will present here what MEMS from ST can do to enable this technology, but we all have a big responsibility. We have a big responsibility to build a world that is more human. We don't want to build a metaverse where we have to flee because the reality is getting bad, worse, pollution, or difficult for everybody. So I wanted to tell this just maybe to get some oxygen and start, and because it was the experience I had this morning. So let me start with the presentation. Again, STMicroelectronics, we are still with the bucket of sands. So we are still building from silicon, from the sand, and we build nice devices that helps developing the technology, in particular augmented reality and extended reality. As per the title of my presentation, I will show you how the MEMS are helping to merge the life with the extended reality. So how the technology can enable what Tom so many years ago was even visioning as a future. So ST is a creator of technology. We work with the sand, I was saying, lots of R&D and patents on the electronics, but we also have a commitment to social responsibility. And that's where I believe, again, it's fundamental. We need to work together for a better world, not to escape from this world into a virtual better one. And a good point is that ST, since the beginning, before the AR buzz, we put in our brand, in our name, the life.augmented. So as a company, we want to bring value. We want to bring a positive contribution to life with the electronics and the technology that we are working on. So the example, and again, the inspiring presentation from Tom before, it's exactly in this line of sight, and we want to continue in this journey. And that's why we are sponsoring such events as well, where we believe the importance of contributing with universities and other communities, it's fundamental. Talking about MEMS, it's nice. I show here an evolution of MEMS technology, microelectromechanical system, because MEMS basically are at the core of the technology of the new innovations in the last 20 years. If we think about the beginning of 2000, with the MEMS, miniaturization of accelerometer gyroscopes, moving from kilograms of devices to a few millimeter devices and very light, we enabled at the beginning of 2000 the smartphone. Just adding an accelerometer, you could turn the phone and having the display rotating, for example. So we enabled the phones to become smartphones. And we see all the evolution. I don't go into these details, but it's important to see that we believe now with the sensors and the actuators, we are at the verge of another big jump in the technology, where basically with micro mirrors, we can enable the display for the future. We are already enabling the display of today, and we see MEMS mirror as the solution to miniaturize and helping building all the wearable glasses that can fulfill the performances and the requirements of the users. Just an example of what kind of sensor and actuators can be and are enabling smart glasses. You can see from, of course, all the motion MEMS, the microphones, or the actuator side, like the MEMS speaker or the MEMS mirror. I will talk more and more in details later on. What is XR? XR is, we are talking about digital world. So the extended reality is a digital content that is augmented our experience and our reality. But at the extreme, the reality is analog, okay? We know that the reality is analog. And so sensors and actuators are the borders of our connections of the system connection to the reality. So a sensor is something that detects a physical change and translates it into a digital signal to be processed, to be sent to the cloud, to be analyzed, to be shared with someone else. And then, as a result of this sensing, actions can be taken, and those actions are basically, again, a digital signals going into an actuator that is then moving something or is doing something. So that's where we position our MEMS technology, so at the limits, at the border of the interactivity of the interactive systems. Interesting, we see, as I say, in the last 20 years, different eras of MEMS related to the use cases. And we help change it with MEMS, the paradigm of the technology. So we like to see that the first decade of 2000 was what we call the offline era, where basically functions were miniaturized. MEMS function miniaturized basically the functions of sensing or actuating, and localized in the mobile phone, as I make an example, we're enabling more and more useful application. Let me make an example, like the Nintendo Wii is a game. When we started with Nintendo, we enabled them with the motion MEMS to change the way of playing. Smartphone was another example. This was the first decade of 2000. Increase of performances localized, offline. In the second decade, so from 2010 and to 2020, so up to now, we moved to the online era. So where the single sensor or actuator has been replaced by a sensor node. The need of connectivity, of processing, the cloud is helping all the power of calculation and data storage. That requires sensor nodes everywhere and capability of low power miniaturization, power consumption, and RF connectivity. Today, we see that in this new decade that just started now, we see what we like to define, we use this term now in ST, the OnLive era. So basically, we need both. There is a fusion of what is in the cloud and what you need to process locally for very short latency. I have 2 slides to go into more details about those 3 eras, and maybe it's better to go through those slides in order to show you what do they mean. First of all, as I say, offline era, introduction of accelerometer in all the tools, washing machine for vibration compensation, or gaming, as I mentioned, or the mobile phone. This is an example that changed the paradigm of the technologies in the first decade, as I was mentioning. The OnLive Era, as I say, the addition of microcontroller capability to the sensor. So intelligence added to the sensor, but most important, RF connectivity. And here you can see the utilization, the use of those technology in industrial application to send data and to be able to process those big data where the power of calculation is. And the most interesting, that's where I want to jump into, is the OnLive Era, where basically, as I mentioned, the latency is fundamental. When we have all the sensor in our glasses, we talk about extended reality, we have all our sensor in the glasses, and we move our head fast. We don't have time to send to the cloud all the sensor data and to process them and say, okay, you move your head on the right, so the object that was there has to move on the left to give the impression that it's not moving, it's still on the table. So local, low latency processing and fusion with the cloud where is needed with local processing capability and low latency, it's fundamental. All of these in super low power, miniaturized. Don't forget we're targeting all the wearable glasses at the end. So this is where we are today, and we see another example I put here I like, it's the LiDAR. LiDAR system for safety in the autonomous driving. It's another big example that is also using MEMS technology, like MEMS mirror for laser scanning. That's where you need to process in milliseconds the understanding of the environment, the situation, and be able to react, to change the steering wheel position, or to brake for safety reason. How can MEMS accelerate this journey to XR? Again, I'm focusing here on the MEMS technology at ST, and this augmented reality, as Tom also was mentioning, is coming, is here. We don't have the volumes yet. There is a consensus talking to the big players that these volumes will come in 2023, 2024, 2025. How can we enable and accelerate this journey? It's fundamental innovation. And innovation is not only on the component side. So as a company doing semiconductor and silicon, we are focused on innovation on our product. But it's fundamental to start from the user needs. And that's why we strongly believe in what is called open innovation. So working together with partners in the industry, in the university, and being able to understand the user needs. User requirements are at the foundation. So we need to fulfill at the end our end users. And to do that, we need to partner. Ecosystem is the magic word. I will show you later what we try to do and what we built to enable this ecosystem. This is an example where we are today. Second point, we need to build a reference design. We need to enable users, enable developers with the technology to build the content and the technology for the end user to be mass-produced at the end. And of course, last but not least, improving the MEMS technology. MEMS technology has to continue what it did in the past, miniaturization, low power performances. Because only with that we can move from the big Darth Vader helmet that Tommy was presenting to those size of glasses. We're talking about 55 grams of glasses that can show and present augmented information all day long. If I go to an example of MEMS, just to start at the core of the augmented reality, we talk about MEMS mirrors. So a laser beam scanning technology is used for displaying into a retina or a waveguide, and it's a technology already available. And as you can see, there are some examples where MEMS mirrors are used within some of the augmented reality product today in the market. HoloLens 2 is an example here, or the North Gen 1 that you know the company has been acquired now by Google. And those companies, they're already using for completely different application. So for enterprise, augmented reality application, or for all the wearable, they're using a laser beam scanning system because of the intrinsic capability of those MEMS technology to be miniaturized and provide performances. Other example I can see here, Intel RealSense or the LeddarTech LiDAR system we are working together with. It's a other fundamental example where mirrors are used today. And what I like a lot is this AccuVein application. I love it because it's already an augmented reality application. It's a medical system with a mirror scanning system and 2 lasers, one infrared and one colored laser. Here is red. In the final product, they selected the green. Basically, you can scan the vein position and paint the vein on your arm, on your head, or on your foot to help, for example, blood drawing for elderly people or kids where it's difficult to find where the veins are. And so the error rate is very high. So that's what I like on augmented reality, when you can really help people and help the user experience. Let's go and focus a bit down. We talk about the need to support the user experience first. So starting from user experience, what do we want from those glasses at the end? We want the field of view. We want a big field of view. We want a resolution. Tom was giving a nice list of requirements. Immersion, and then durability, low power. You want to keep them all day long, but they should not be that shape at the end. They must be light. And how a company like ST can help with a MEMS mirror, because all the requirements I put on the table are against some of the physics. So we need to increase the frequency of the mirror if you want better resolution. We need to increase the opening angle of the mirror. So we need more voltage, more frequency, more power to go and achieving what the users require us to do. And so I put a simple formula here, CV square F. You know very well when you have to move a resonant mirror, this is the power consumption. If I need to open more, I need more voltage. More resolution is the frequency. So power consumption is one of the critical items where we need to innovate and where we need to build the full solution, bring the full solution to where the user requires it to be. So where did we start from? And that's, I believe, the fundamental step. As I say, we need to start building an ecosystem. And ST funded the Laser Alliance. Those are the co-founders of the Laser Alliance. And the reason behind the Laser Alliance was bringing together the different components to enable a full system integration. MEMS or laser beam scanner is not enough to make an augmented reality system. We need to build together the waveguide. We need to build lasers. We need to be able to build a manufacturing small module that can be integrated into real glasses. So the first founders had the idea to put together all these competencies and working holistically, simulating and building a system that get trade-offs from what a mirror, a MEMS can do and what a waveguide can do. And we are working towards the creation of a system that will enable the performances that are required. As a matter of fact, together with the Laser Alliance, we built a small module. We have the smallest optical engine that can be generated for high resolution or the required resolution. So we are able to achieve a very small 0.75 cubic centimeter module, working on the different technology, on new lasers, on new MEMS mirror. And this is just an example I want to bring here, where moving from what we have today and what we are demonstrating at CES in a few months, we are improving the performances. I don't go into those details, but it's important. Field of view is increasing. The resolution is increasing. The size, the volume is decreasing, and the power consumption is 50% less. This is enabled by the innovation at all the level. And for what concerns ST, the innovation is on the material side, on the piezo side. And piezo is the actuator technology of those MEMS mirrors. So we are working with the research, a university center in Singapore, IME, the Institute of Microelectronics, with a vendor of tools. We built what we call Labinfab, lots of investment to help the scalability of those technology. So the target is really to move from what we have today to something that is more performant and lower power. I don't go into the video. I'll leave you. You can Google and find on YouTube. It's a nice video on what we are building in this Labinfab, where university and semiconductor company like ST, equipment vendors are fusing together all the and joining forces to build the right material and technology on the MEMS side to enable what Tom was presenting as a desiderata for the user experience. And to show why this is important, again, this is a roadmap on the technology. It's a piezo technology roadmap. You can see how we can move on actuation force. So the piezo is measured by the displacement force, how much you can displace a mass per voltage applied. By doing this, we already see how our current MEMS mirror used in the first projector that we have today can be reduced in size or in power consumption. That's the target. Okay, I see I have the last two slides, and basically the most important part is why we believe that laser beam scanning is the right technology to go into small form factor is because, as what I just mentioned, we have a scalability. We can increase the resolution, we can increase the frequency, the opening angle, working on the material, and that's where is our core technology, core know-how. Working on the material, we can do that, reducing the voltage, reducing the power consumption of the system. So we can cover with small form factor and low power the performances that are required. A fixed pixel display cannot do that because either you increase the die size because you have all the pixel in front of your waveguide, or you squeeze the pixel and reduce the brightness. So those are basically just to give you a little bit of a flavor on why laser beam scanning is fundamental. I close here basically, and I want just to give you the takeaways of today out of what I just started in my presentation of the importance of the real reality and helping with augmented reality. The few takeaways I want to show you and give you today is that we believe MEMS mirror laser beam scanning solution are the solution that will enable all the limitations and the challenges that also Tom was mentioning before. Verge accommodation, the possibility to have retina scanning for high resolution, high field of view in a form factor that is for the users, that is for us, that is this one, what I'm wearing now for augmented reality. MEMS technology improvement is helping the scalability, as I just mentioned, and most important is the partnership among all the players in the domain from application standpoint, content standpoint, semiconductor standpoint, and the universities and the academic world, because we want to build something that is useful for the world. It's not just technology for technology. We don't need that. Thank you. I finished.